Okay, hello everybody. Today we are looking at something called dynamic equilibrium. Okay, so this is Unit 9, Lesson 5. So our intention today is to describe chemical dynamic equilibrium. We're going to talk about other types as well. In terms of the concentration of reactants and products and the rate of the forward and reverse reactions. Okay, lot to unpack there. So let's start with a little bit of a review and a do now question. A couple questions. Um, Actually, like five. So it's kind of a longer one. But definitely take the time to pause. So, what you're doing in the first question is I've given you four ways you could change a reaction. And I want you to tell me how that's going to affect the speed of the reaction or the rate of the reaction. Right? That was from yesterday or the last lesson on reaction rates. Okay, so, and number two is multiple choice, and that's a simple, right? You pick one of the four choices there. So go ahead, pause the video, try these out as a nice refresher because these are going to be important. Okay, so hopefully you paused, right? So number one says describe how the rate of a reaction will be affected by the following changes. So one, if you increase the concentration of the reactants, you're going to speed up the reaction. It's going to increase the rate, right? That means more collisions. That means the reaction will happen faster. Two, if you decrease the temperature, right? If you remember from the last lesson, increasing the temperature increases the rate. So decreasing the temperature is going to slow down the reaction, right? It's going to reduce the rate or decrease the rate of the reaction, right? That means the particles are moving slower. They're going to run into each other less often. They're going to react less often, and therefore the reaction will slow down. Number three, decreasing the surface area of the reactants. If you remember, right, if we increase the surface area, that's like taking a pill or something and crushing it up so that it has a higher surface area so that when you put it in water or whatever you're putting it in, it reacts quicker. So if you increase surface area, it's going to increase the rate of reaction. If you decrease the surface area, it's going to slow down the reaction. And finally, adding a catalyst. Okay, so when you add a catalyst, it always speeds up a reaction, right? And if you remember, it does that by lowering the activation energy necessary to get that reaction started. Okay, so hopefully that was a good review for you. You got most of those. That is from lesson 4, if you need a review on the different factors that affect reaction rate. Okay, number 2. Which event must always occur for a chemical reaction to take place? All right, so hopefully you recognize the wording, okay? You don't always need a precipitate, you don't always need a gas, you don't always need a catalyst. However, you do always need effective collisions between reacting particles. So number 2 is C, right? You're going to see this phrasing is repeated over and over again, right? You'll see it basically like this every time. But you know, if two things are going to react, they have to run into each other. They have to have an effective collision, right? Colliding with the proper amount of energy and the proper orientation. Okay, so that's all review. A lot there, though. Feel free to go over that again, right? You have the power to rewind and play again. All right, so let's start talking about this thing called dynamic equilibrium. And we're going to start by using an analogy and then answering some questions based on that analogy, right? So let's picture a manufacturing plant, right? Acme Manufacturing. They've been restricted to 100 employees in the building at one time. Maybe there's some sort of pandemic going on. So throughout the day, 20 employees go on break each hour as 20 other employees return from break, right? Which is kind of sort of depicted. It just looks like 3 people, but right. So here's our situation. There's only 100 people can be in the building at once, but that's it. So every hour, 20 of people inside the building go on break, and then 20 people that were on break come in to start working. Okay? So let's break this down a little bit. And it's going to seem a little simple at first, but you'll see why I'm doing it. So how many employees move in and out of the factory building each hour? Well, that's just right from the the sentence there. 20 move in, 20 move out each hour, right? Yeah, that's just what it says. Number 2, are the employees who move in and out of the building each hour the same people? Oh, and you can also pause these before I answer them, right? That's all. That's super helpful for you. It's a little more work, but it'll make this stuff stick better. So hopefully you noticed, right? They're not the same people, right? There's 20 people in the building, in the factory, and they go on break. They leave, and there's 20 different people that start working. They come back from break. So it can't be the same 20 people, right? 20 are going on break, 20 are coming back from break. So the people that move in and out are different. They're different people. Now, does the number of employees in the building change from hour to hour? And explain your answer. What do you think? Well, no, right? It's not going to change. There's 100 people in there, and if 20 leave at the exact same time that 20 enter, right, there's still going to be 100. Okay, and we are assuming that it is perfect timing, right? Nobody's late, everybody's on time, and the second those 20 people walk out the door, 20 other people walk in the door to start working. So at any given moment, there's 100 employees, not always the same 100 employees, but there's always 100 because when 20 leave, 20 enter, right? So you're never down any employees. So the factory can keep going. Now, over the course of a day, this one's very important, right? The employees in the manufacturing plant are said to be in a dynamic equilibrium. All right, so based on your understanding of how the staff move in and out of the manufacturing plant, try to explain what is meant by the term dynamic equilibrium. And I do urge you to pause and really think about what we just talked about and try to explain. We just described dynamic equilibrium, so maybe try to come up with a definition for yourself before moving on. Okay, so let's try to break this down. So dynamic equilibrium, right? Dynamic means there's movement. And here we have movement, right? If we think about it, what is the thing that is, staying equal? What's equal in that dynamic equilibrium? Well, you could say it's the amount of people coming in and going out, right? There's always 20 coming in and 20 going out. So the number of people leaving is equal to the number of people entering. Okay, but there's movement, right? That's the dynamic part. We could also say, right, there's always 100 employees in the factory at any one time. Okay, so as we transition away from this analogy and into like the actual chemistry definition, it's not that much different. So during a dynamic equilibrium, okay, what we say that the concentrations do not change. They don't have to be equal, but they don't change, right? At any given moment, there's 100 people in the building and 20 people on break, right? Those aren't equal numbers, 100 in the building and 20 on break, but they don't change. So we say the concentration, and you could think concentration of people in the building versus the concentration of people on break. It doesn't change. They're not equal, right? 100 does not equal 20, but they don't change. So concentrations do not change. So what's equal? What's equal is the rate at which people are exiting and entering the building, right? It's always 20. So as 20 people come in, 20 people go out. Okay? So in dynamic equilibrium, the concentrations do not change, and the rate of the forward and reverse reaction, and that's our going into the factory or coming out of the factory, that's the thing that's equal. Okay, so hopefully that breaks it down a little bit. We're going to talk more about it, but feel free to replay. I'm going to move on here. So let's talk about chemistry, but not too intense. Okay, so let's talk about reversible reactions in terms of this dynamic equilibrium. So you might think, right, that every reaction just happens, right? We set off a reaction, it's done, and that's it. In reality, most reactions, they don't go all the way to completion, and they actually go backwards while they're happening in the forward direction. So it is a little more complicated than it appears at first. So let's simplify it a little bit. So we have a gas called A, right? That's the G stands for gas in the parentheses. A is turning into B, but also notice this looks a little different now, right? It's not just a one-way arrow. We also have B turning back into A. All right, so take note of, I think that's my first question here, right? What is the significance of that double arrow? Well, that means that this system is at equilibrium, okay? We have A turning into B and B turning into A. Now, let's imagine that the reaction above starts with 100 molecules of A and 0 molecules of B. Explain why the concentration of A will never reach 0. Pause, right? Try to answer it. Well, it'll never reach 0 because as the A starts to turn into B, right? We start off with 100, then there's 99, 98, 97. They start reacting and turning into B, but then the reverse reaction also happens. B starts turning back into A, right? So we have A and it starts to decrease as it turns to B, but then it starts to get kind of like refilled, right? A starts to come back as the B turns back into A, right? Because it's a forward and a reverse reaction. Okay. So, at dynamic equilibrium, let's describe these things. This is kind of like the key point here, okay? So this number 3 question is pretty big. All right, you're definitely going to be, you'll be quiz tested on this. At dynamic equilibrium, let's describe the concentrations of A and B. Okay, so, right, if this is truly at equilibrium, that means, just like, remember back to the analogy, how many people are in the factory? Well, there's 100. How many people are on break? Well, there's 20. Those are the concentrations. We have 100 in and 20 out. So we'll say A is in the factory and there's 100, and B is outside of the factory and there's only 20. So those concentrations, they're not equal. That's the biggest misconception here, right? 120 are not equal. So the concentrations do not have to be equal, but they are not changing. Okay, so at dynamic equilibrium, the concentrations of reactants and products do not change. Okay, they do not have to be equal, but they are not changing. Right, there's always 100 people in the factory and 20 on break. Now, at dynamic equilibrium, let's describe the rate of the forward and reverse reactions. Okay, so again, we can think about the factory. 20 people come in, 20 people go out. Okay? In this scenario, A turns to B, and B is turning into A. And if it's truly at dynamic equilibrium and these concentrations aren't changing, then the rate of the forward and reverse reactions must be equal. That's what's equal in dynamic equilibrium. Okay? That's a key point here. So I'll say it again. Dynamic equilibrium, concentrations do not change, and the rate of the forward and reverse reactions are equal. So it's going to look like nothing's happening from afar, right? If you just took snapshots of the factory floor, if there's always 100 people, it kind of looks like nothing's changing, even though we know that 20 people are coming in, 20 people are going out every hour. And I do want to say one other thing about this. Okay, so why not just call this equilibrium? Why do we have to call it dynamic equilibrium? Well, there's also a thing called static equilibrium. Static means not moving. But we know in this scenario, there's lots of movement, right? There's A turning into B, B turning into A. But also, if you think about the factory example, we have 20 people going in, 20 people coming out. It's dynamic because there's motion. Something that's like static equilibrium would be like buildings, right? They all the forces that hold them up, right? There's equal and opposite forces, right? There's that downward push of the building on the ground and the upward push of the ground on the building. That's equal, but nothing's changing in that situation, right? There's no constant movement. That's called static equilibrium. Okay, so that's the difference here between static and dynamic. For us in chemistry, it's always dynamic. There's always movement, right? The only time there's no movement is at 0 Kelvin, if you're kind of a throwback, right? 0 Kelvin, which is the absolute zero, where particles stop moving entirely, right? Okay. So again, right, as long as you get the answer to number 3 here, that's the main point. The last 2 minutes of me talking is just a little extra. Okay, so here is kind of a way to visualize dynamic equilibrium in a couple graphs. So, take a step back, let's take this in. So let's look at this first one. We have rate on the y-axis and time. So this is as the reaction goes on, and this is measuring the rate of the reaction. So here is A turning into B, and you'll notice at the start, it's really high because we start off with all A. And if all we have is A, well, yeah, it's going to go in the forward direction, right? But as that happens, the rate starts to slow down. And look at the other rate. The rate of B turning back into A starts at 0 because we don't start off with any B. But as B starts to increase, as the concentration of B starts to increase, then the rate at which B is turning back into A starts to increase until we hit dynamic equilibrium, which starts right here, where the rates are equal. Okay, that's different than concentration, which is what we see in this second graph. Okay, this is the concentration of A. We start off with a lot of A and no B, right? As A gets used up, the concentration starts to go down. As B starts getting produced, the concentration goes up until we hit dynamic equilibrium, and the concentrations stay constant but not necessarily equal. Okay, so the rates are equal at equilibrium, and the concentrations are constant. So that these brackets, that just means concentration of A. So anything, if you see these brackets at all, that just means whatever's inside them, it's talking about the concentration of A. Okay, so same takeaway as the last slide. Dynamic equilibrium, rates of the forward and reverse reaction are equal. Concentrations are constant, or they don't change. Okay? All right. So a few more things. Not as complicated as the last. So there's different types of equilibrium, dynamic equilibriums, phase, solution, and chemical. Right? We've already talked about chemical, but let's look at all of them together. So in phase equilibrium, and phase we're talking about states of matter, right? So it's a balance between two opposing phases of matter. This is when we have phase changes occurring at the same rate. This happens all the time, okay? So this could be boiling and condensing happening at the same rate. Melting or freezing happening at the same rate. Sublimation or deposition happening at the same rate. These are all just phase equilibrium. So a good example of this, and to have phase equilibrium, you have to have a closed container. So picture a water bottle, shouldn't be hard. That's about, half full, okay? It looks like nothing's happening in that water bottle, right? It's just sitting on the table, the cap's on, nothing's happening. But in reality, a whole bunch of stuff is happening. But it's at dynamic equilibrium, so it looks like nothing. But what's really happening is a phase equilibrium, right? That liquid water in the water bottle is turning into gaseous water in the top of the water bottle. But at the same rate, the gaseous water in the top is condensing back into liquid. So there's actually tons of things happening inside of a water bottle just sitting on a table, but it looks like nothing, right? That's the kind of the cool thing about equilibrium, dynamic equilibrium, is that there's movement, it's dynamic, right? But it looks like nothing's happening. But if you were to zoom way in, right, at the surface where the water meets the air, or the gas above the water, there would be water molecules going from the liquid stage to the gas stage, and the gas stage to the liquid stage. But the key point is, because it's happening at the same rate, it looks like nothing's happening. If you were to take the top off the water bottle and let the gas escape, then eventually all the water would turn into gas and leave the system, right? That's not dynamic, that's not equilibrium, because the concentrations aren't remaining the same, right? You've opened up the system, you're letting the water escape, the gaseous water, the water vapor escape, so that the liquid water keeps turning into water vapor, but the water vapor is escaping and it's not turning back into liquid water. So that's, right, you have to have a closed container. Okay. There's solution equilibrium. So remember, a solution, we have a solute dissolved in a solvent. So this is when a solid, or it could be a gas, dissolves in a liquid to produce a saturated solution. Okay, it has to be, to have solution equilibrium, it has to be saturated. We could talk more about that in a second. This is where the rate of dissolving equals the rate at which the solid leaves the solution, and we call that crystallization. So picture, let's see, your iced coffee, right? It's a nice summer morning. You go down to the bodega, you get nice coffee, you get sugar in it, but you have all that sugar stuck at the bottom, right? Because it's an iced coffee, and we know things don't dissolve as well in colder temperatures. So you have all that sugar stuck at the bottom of your iced coffee. Now, it might seem like nothing's happening, but in reality, that solid sugar at the bottom is dissolving into the liquid at the same rate as the sugar that's already dissolved crystallizes into solid sugar at the bottom, right? It looks like nothing's happening, but within that iced coffee, there's so much movement, right? We have that solid crystallized sugar at the bottom that's dissolving, but also we have the sugar that's already dissolved, right? It starts to crystallize on the bottom, but it looks like nothing's happening. It's just happening at the same rate. So there's a lot happening there as well. But remember, it has to be saturated, because if it's not saturated, then it's just going to keep dissolving until it is. So you can't hit equilibrium until the solution is saturated, right? Because if it's not saturated and you put more sugar in, it's just all going to dissolve and none of it is going to crystallize. Okay? So to have solution equilibrium, it must be saturated. Or another way to say that, right? It must be kind of like full of the solvent, right? Kind of what saturated means. And then chemical equilibrium, we've already talked about that. That's when the forward and reverse rates of a chemical reaction are the same or equal. Okay? So it's always about the rates. In phase equilibrium, it could be, liquid turning into gas and gas turning into liquid at the same rate. For solution, it's the solid or gas is dissolving at the same rate at which it's coming back out of the solution, right? We call that crystallization if it's a solid. And then chemical, forward and reverse reactions, the rates are the same. Okay? All right. So I know there was a lot. There's kind of a lot in this lesson. And then the next lesson does build on this stuff. So definitely feel free to spend a little longer on this lesson. I believe you're seeing this. Yeah, you're seeing this on Friday, tomorrow for me. But I'm going to give you, next week is our quote-unquote spring break. So I'll give you plenty of time to get this done. You won't have to do it. You won't have to finish the lesson or the homework until the 20th when we, come back, quote unquote, again from spring break. So all next week I'll have office hours. We'll be able to discuss this stuff in more detail because I'm sure there's questions. So here's your check for understanding for today. Definitely pause here. All right. And when you unpause, I will be going over it. Okay, welcome back. Hopefully you paused and it's not super awkward and me just continuing the conversation with myself. So we have a reaction here. The following reaction has reached equilibrium. Okay. We have, it's this reaction. We know this one. This is hydrogen gas combining with oxygen, turning into water. But this time, look, so this is another way to draw that double arrow, right? We saw it looked like this, right? You could have two arrows, one on top of another. You can also draw it like this, where it's a double-headed arrow. They mean the exact same thing. All right, so in reality, in this reaction, the gas, hydrogen and oxygen are turning into water, but water is also turning into hydrogen and oxygen. And it's telling us it's at equilibrium. So describe the concentrations of H2, O2, and H2O. Are they equal? No, they are not equal, but they're not changing. They are constant, right? So there might be a lot more hydrogen, a little bit of oxygen, and some water. They don't have to be equal concentrations. In fact, they probably are not, right? That would just be a coincidence. But the concentrations do not change. That's it. End of sentence. Okay. Compare the rates of the forward and reverse reactions. It says it's at equilibrium. Therefore, the rates are equal. That's the equal thing, right? Forward and reverse reaction, the rate is equal. Okay. Number 3. Okay, now we're done with that top equation, I guess. Identify the following as phase, solution, or chemical equilibrium. Okay, this one's probably a little tricky, right? You really got to look at these different things. So this first one we have hydrogen gas, iodine gas turning. Okay, this is very clearly a chemical reaction. You know how I know? I got substances here, and they're different than the substances here. If you have two different substances on each side of this, right, there is some kind of chemical reaction that had to have taken place. That's a chemical equilibrium. Okay, we have CO2 gas at equilibrium with CO2 aqueous, which means dissolved carbon dioxide. Okay, so it's the same substance changing, and now aqueous means dissolved, right? So that's a solution. So this is solution equilibrium. And this right here is exactly the equilibrium that occurs in a closed can of soda, right? Carbon dioxide, we say it's carbonated. We mean it has dissolved carbon dioxide. And if the can is closed, there's some gas above the liquid, and it's dissolving into the whatever the soda is. Let's call it, Coca-Cola. But also that gas is coming back out. It's just happening at the same rate. So that's solution equilibrium. This one, we have chlorine gas turning into chlorine liquid. Well, that's a phase change. That's phase equilibrium. Finally, we have sodium chloride, salt, right? Our good old salt. And it's an equilibrium with dissolved sodium ions and dissolved chlorine ions. So this, right, anytime you see that aqueous, it's going to be solution. Okay, so that's a solution equilibrium because that, right, this is salt dissolving and then recrystallizing back into solid. Yeah, okay. So number 4, oh, good, just a multiple choice. This is a key question, though. A solution at equilibrium must be saturated. It absolutely must be saturated because if it's not saturated and you add more, I don't know, sugar, whatever it is, it's just going to dissolve. It's not going to come back out. You're not going to have any sugar at the bottom, right? This would be like if you somehow got the perfect iced coffee and there's no sugar at the bottom. It probably means they didn't put enough in, right? So that's not saturated. So if you add more, it's just going to dissolve, right, until you hit that saturation point. Then you get the sugar at the bottom that's dissolving as it's also recrystallizing out of the solution. All right. So I know this is a heavy lesson, especially compared to the last one. So feel free, to look over it again, and you have plenty of time to get this one done. Come on into office hours. You can end the video here. There is a challenge question coming up. But if you're done, that's awesome. Try the homework. I'll see you later. Okay. So challenge question. If you stuck it out this long, good for you. Predict at least 2 circumstances or outside influences that would cause a system at equilibrium to change the concentration of its reactants or products. So go ahead and pause. See if you can come up with 2 circumstances. So I'm not going to go through every circumstance. I'll go through some ones you probably thought of. This is actually the topic of our next lesson. But essentially, right, you could, if you added, you could add more reactants or products. That's probably the simplest answer, right? If I put more reactants in, it's the reaction's no longer at equilibrium, right? It's going to make more products. If I put more products in, it's going to go reverse and make more reactants. I could also change the temperature, right? What else could I do? I could also take out, right? I did say change the concentration. I could add more, or I could take out some of the reactants or take out some of the products, right? And that'll cause an imbalance. There are other answers to this. If you're really curious, look up Le Chatelier's principle. And if you don't know how to spell that, it's in your the unit overview as one of the lesson titles, okay? All right, so yeah, that's going to be it for today. I'm going to end the video here because I feel like I'm going a little long. All right, please come to office hours with questions. Shoot me an email if it is outside of office hours, and I will respond as quickly as possible. Okay? All right. See you guys later.